In this example, we're going to derive the area formula for the ellipse. To do so, we're going to determine the area contained inside of the ellipse, x squared over a squared plus y squared over b squared is equal to 1. This would be an ellipse centered at the origin. The length of the minor axis would be 2b, and the length of the major, oh, that is not proportional at all. Oh boy. Well, we're going to pretend, because making believe can be fun even if you're an adult. Now, assuming, under the terrible assumption in this case that this thing is actually drawn correctly, some symmetry can be seen here. So the strategy that I'd like to use is we're actually just going to determine the area contained within the first quadrant, and then we're going to multiply that by 4. Double it to get it over to the left side as well, and then double it again to get the portion that is below the x-axis. So first thing we're going to do is we're going to parameterize the ellipse. And for this, I'm going to call back to the video on the Common Parameterizations, Part 2, that talks about how to parameterize conic sections. The common parameterization that we're going to use is that x is going to be equal to a times the cosine of t, and y is going to be equal to b times the sine of t. Now, if we wanted to do the entire ellipse, we could say that t goes from 0 to 2 pi. Using this definition is sort of the standard from what we see back in trigonometry. This is t equals 0. This is t equals pi over 2. T equals pi. T equals 3 pi over 2, and then back to 2 pi. Now, what this means for us is that if we're interested in just what's in the first quadrant, then we'd be just interested in the portion between t equals 0 and t equals pi over 2. So the first way that we're going to set this up is assuming that y is a function of x. So what we're going to do is say that the total area is going to be equal to 4 times the definite integral, and we'll just say from t1 to t2 of y of t times x prime of t dt. This was akin in our last video to saying f of x times dx. So this will be 4 times. We'll worry about the bounds in a second. Y of t would be equal to b times the sine of t. X prime of t dt is going to be the derivative of a times the cosine of t. Treating a as though it's a constant multiple, this will be negative a times the sine of t dt. Now, as far as the bounds are concerned, I mentioned this in the last video and said this will be important in the next video. The bounds on x are supposed to go from left to right, regardless of what t value is associated with which. In order to go from left to right, that means the lower bound would be associated with t equals pi over 2, and the upper bound is associated with t equals 0. This seems backwards. However, there is a property of definite integrals that says if you have a negative 1, you can use that negative 1 to reverse the order of the integration. As such, we're going to do exactly that. We'll take the constant a and the constant b, factor them outside of the integral to get 4ab. We'll use the negative sign to reverse the order of integration, or the bounds as it were, and then we'll be left with the sine squared of t dt. Evaluating this can be done using a power-reducing identity, and let's go ahead and proceed. So this will be 4ab times the definite integral from 0 to pi over 2 of power-reducing identity for the sine squared is half of 1 minus the cosine of 2t dt. This can be evaluated fairly straightforward. I can take the 1/2 and pull it outside, combine with the 4 to be left with 2ab. And then we integrate. 1 becomes t, and the cosine of 2t will become the sine of 2t divided by 2. From lower bound 0 to upper bound pi over 2. The only non-zero term we're going to get is when we plug in pi over 2 for the t. This will be 2ab times pi over 2 minus the sine of 2 pi over 2 minus a lot. of 0, giving us a final answer of pi times a times b. You'll notice the similarity between this and the area of a circle formula. If this ellipse were actually a circle, then both a and b would be equal to the radius of the circle. And that would be pi times r, rather than pi times a times b. So very closely related to the circle formula. Now, in the event that I wanted to treat this as though x were a function of y, then we could also say that the integral is 4 times the integral from t1 to t2 of, this time it would be x of t times y prime of t times dt. Now with that in mind, x of t was equal to a times the cosine of t. And y prime of t would be the derivative of b times the sine of t. That would be b times the cosine of t times dt. Now, treating y as our independent variable, we would want to go from lower y value to upper y value. And the values of t associated with this would be t equals 0 and t equals pi over 2. So this one would not show up backwards. This one would just be 0 to pi over 2, no problem. Once everything is sort of algebraically fixed down here, this will be 4ab times the definite integral from 0 to pi over 2 of the cosine squared of t dt. The process is nearly identical to what we just went through from here. Literally the only difference is going to be the power reducing identity will involve a plus here. Nothing else about the process is going to change, and we already know what the answer is going to be, so I'll just let you know. Pi AB will once again be your final answer. If you'd like to try working through that power reducing identity, I would encourage you to do so. However, you're under no obligation to do so.